Here's our worksheet that we are looking at, and I should have said when I ended the last video that you should have completed problems 1 through 4 in the worksheet. So if you haven't done that, you might as well stop now, although some of them might be a little bit confusing before you see some examples worked out. So here was a situation where we launched a ball upward with a 30 meter per second initial speed. We're going to take our system to be the ball plus the earth, where the gravitational force between them is an internal force, and we're going to assume air resistance does a negligible amount of work in that case. And our goal is to find the height that it reaches using energy methods. In other words, we know we could use kinematics, but let's try to use our latest work-energy relationship, which looks like this. The net work done by all external forces on our system is the change in kinetic plus the change in potential energy. And in this case, our only external force would have been air resistance, but we're assuming it does a negligible amount of work, and so therefore the left-hand side is 0, and we would say mechanical energy is conserved. What we're going to do is just expand out the right-hand side, write it out in more detail. Change in kinetic energy is 1/2 mv final squared minus 1/2 mv initial squared, where m is the mass of the ball. And the change in potential energy, here we use the gravitational potential energy associated with the gravitational force near the surface of the Earth, and that was mgy. So here we have the change is mgy final minus mgy initial. The first thing I can do to simplify this is just to cancel the common factor of mass. In other words, factor out the m on the right-hand side in front of everything, and then divide both sides by m. The left-hand side doesn't care. If you take 0 and divide by m, you still have 0, but in the right-hand side, it just makes those m's disappear, which simplifies our work. Second simplification we can do is to realize that in this case, if we want to know how high up it goes, I'm going to define my initial to be right when I release it and it has that 30 meters per second speed, and final to be the highest point. And when it's at its highest point, its final velocity will be 0. So this whole first term goes to 0, simplifying our life. All right, let's do a little bit more. What I can do now is solve for y final minus y initial. In other words, I could factor out a g in front of this, and I would get g times y final minus y initial. And it is that y final minus y initial that I'm after. How high does it go above the release point? That's what y final minus y initial is. And if I solve for what that is, I had a minus 1/2 v initial squared. I can put that over with a plus sign over here, plus 1/2 v initial squared. And then I've got to divide by g. And when I calculate that quantity, I get y final minus y initial is 45.9 meters. All right, part B. Let's change our system now and make sure that we get the same result. I'm sorry, not the same result. I'm asking a different question here, but we're not going to take the same system that we did before. Rather, we're going to change our system to be just the ball itself. Gravity, we're now going to regard to be an external force, and the ball is just a particle. And again, we're going to ignore air resistance. The question now is to find the speed that the ball has after it's risen 30 meters above the release point. Again, using energy methods. And here's how we'll approach it. In this case, there's no potential energy to be spoken of because the system is just a rigid particle. There's nothing, no internal forces to associate a potential energy with. So the work kinetic energy theorem applies to that. It's a particle. So here is the work kinetic energy theorem. And of course, we're after that V final. So I'm going to define initial to be just after it's released. Final configuration is when it's risen 30 meters. And let's fill in these details. The work done by the external gravitational force, first thing to realize is it's negative. The gravitational force on the rising ball it's doing negative work because the ball is rising, but the gravitational force on it is downward. And so that's the hallmark of negative work. And we can use our force times distance way to calculate the work done by a constant force because the weight force is constant. So I just get mg times the distance it moves, and I have a minus sign out in front because it's a negative work. And that's equal to 1/2 mv final squared minus 1/2 mv initial squared, We know what V initial is, so I plug that in here. And I've got a common factor of m on both sides, so I'm just going to divide both sides by m and solve for that V final. We want to know what the final speed is if the final y position, or sorry, the distance is moved under the influence of the gravitational force is 30 meters. When I solve for V final after taking a square root, because it was squared over here, I get 17.7 meters per second. Problem 2 involves an ice cube, mass 30 grams, released from rest at the edge. I've got a bowl that's a hemisphere here. I'm just showing the cross section of it. We have to imagine it's completely all the way around, like a metal bowl that's exactly a half sphere, and we place an ice cube just on the inside edge of it, and we'll assume the friction between the wet ice cube and the side of the bowl is 0. So it's released from rest up here, and the question is, how fast is it going as it zooms by the bottom of the bowl there? And we're going to want to use energy methods again in this case. So I'm going to take, there's more than one way to do these kinds of problems, but let's take our system to be the cube plus the Earth. In other words, the cube and the Earth and the gravitational force between them is going to be an internal force, but the bowl is also exerting a force on part of the system that's moving, and I'm going to regard that bowl normal force to be external. We'll assume there's no friction force here. That's the idea of the ice cube. So it's a springy system. There's that invisible springy gravitational force between the ice cube and the Earth, so it's got a potential energy associated with it, so I've got to use our more general work-energy relationship. The first thing to realize is that the bowl normal force doesn't do any work on the ice cube as it's going from the side of the bowl to the bottom of the bowl, because it's always pointing in the radially inward direction, whereas its motion is always in the tangential direction. And anytime a force is always perpendicular to the direction the object is moving, that is the hallmark of 0 work. So even though there's an external force, it doesn't do any work on the moving pieces of the system as it goes from the initial to the final configuration. So the left-hand side is still 0. And the right-hand side, I do the usual old game. I write change in kinetic energy as 1/2 mv final squared minus 1/2 mv initial squared, and the change in the potential energy is mgy final minus mgy initial, and here I factored out the mg because we know y final minus y initial. What do we know? It's released from rest, so the initial speed is 0 if it's released from rest. Also in this relationship, I can divide both sides by m, and that makes the m's disappear, which is kind of nice. And I also know how far it goes in between the final and the initial points. It goes down closer to the Earth. Remember, when we're using this expression for the gravitational potential energy, the convention is that plus y is always up. So in between initial and final, it gets closer to the Earth by 1 radius of the bowl, and we're told the radius of the bowl is 20 centimeters or 0.2 meters. So its change in y coordinate is minus 0.2 meters. That's what this is about. So plugging all that in, what we want is V final, the speed at this final location down at the bottom. And we can solve for that in a straightforward manner, just doing a little bit of arithmetic there. We get 1.98 meters per second as it's moving past the bottom point. Problem 3 involves a mass that is on a frictionless surface, so it can slide horizontally. I just wanted to, it's simpler to imagine this at the surface of the Earth, but there's no other force on this mass that's going to do any work other than the spring force in this case. There's no frictional force that's pulling along the direction that it's moving. So the mass is connected to a wall at one end with a spring constant of 200 newtons per meter, and the other end's attached to the wall, and the mass and spring system is stretched to a distance of 0.4 meters beyond the spring's equilibrium position, and it's released from rest in that position. So we take it in its relaxed position, we stretch it out by 0.4 meters, release it from rest, and we want to know what is the mass's final speed right at the moment it's passing by the position where the spring is completely relaxed. That's by definition, x equals 0. Okay? And in this case, we'll take our system to be kind of everything. The earth that the spring is attached to on this side plus the mass, and we'll take the spring to be an internal force, so it's going to show up as a potential energy in our system. And we'll use our latest work-energy relationship. Sometimes I'll say the system is everything because we've included all forces that might do work and all objects that are specified in the problem. Again, in this case, there are some external forces acting on pieces of the moving system. There's a normal force here, and this object is moving. There's a normal force and a gravitational force. They are both perpendicular to the direction that it's moving, and so they do 0 work. So even though there are some external forces in this case, they're doing 0 work. So mechanical energy is conserved again. We're releasing it from rest, so V initial is 0. In the final position, that's by definition when it passes x equals 0. Here I'm measuring the x of the center position of the block. X final is 0 because it's at the final position of x equals 0. And so using these two middle terms go away because there's zeros in them. And I can solve for, knowing x initial, I can solve for what V final is. That's what we're being asked for here. V final is 8 meters per second when you run the numbers through. Finally, problem 4. Here we've got a 30 kilogram rock released from rest 1 moon radius above the moon's surface. So in other words, the moon has quite a big radius. We're going that same distance above the moon's surface. So it's not close to the moon's surface. We can't just use the force formula mg anymore. We've got to use gm1m2 over r squared if we're concerned about that force. We release it from rest 1 moon radius above the moon's surface, and we want to know its speed just before striking the surface. And we're going to take our system to be essentially everything in the problem. The rock that we're releasing plus the moon, and we'll take that gravitational force to be an internal force. And I'm going to write that in this case there are no external forces to do work for the net work done by external forces. So there's that 0 on the left-hand side. And on the right-hand side, we do the usual thing. 1/2 mv final squared minus 1/2 mv initial squared is the change of kinetic energy. And the change in potential energy involves that formula minus gm1m2 over r. There's no square in the denominator, and it's got that extra minus sign. And I really encourage you to use parentheses to keep track of that minus sign here. So we're doing potential energy final. That has its own minus sign, right? Minus potential energy initial. So we're subtracting off the initial potential energy, and that initial potential energy also has its own minus sign there. Okay. The initial speed, we're releasing it from rest, so that's 0. And the other thing I'm plugging in here is something we know about the initial r and the final r. The final r, we want to know its speed just before striking the surface. So right before it's about to smack into the surface, we'll call that the final configuration, and the initial was when we released it. So initially it was 2 moon radii away from the center of the moon, and the final state is only 1 moon radius away from the center of the moon. Now the first thing I'm going to do is simplify all these minus signs here, right? Minus minus is plus, and this one's minus there. When I do that, and then plug in all the constants here, right? The mass of the rock, the mass of the moon, we know what capital G is, so we know everything about this stuff over here. I can just solve for V final, and we find it's pretty big. Of course, we're dropping it from way above the surface of the moon. It's moving at 1700 meters per second by the time it plunges into the moon. Part B of the same problem, we're imagining launching the same rock from the surface of the moon, and we want to know at what speed could we launch it. So what's the smallest speed we could launch it straight up from the surface of the moon at and have it not ever come back to the surface of the moon? That is sometimes called the escape speed for that particular planet or moon in this particular case. What's the smallest launch speed the rock could have and never fall back to the moon? So we can think about it this way. If I launch it up with a wimpy speed, it's going to fall back to the moon. That's not a big enough speed. If I launch it up with a huge speed, it's just going to go far away from the moon, and even when it's 1,000,000 miles away from the moon, it's still going to have a lot of leftover kinetic energy. That clearly wasn't the minimum. The minimum is when I launch it at just the right speed so that it never falls back, but that as it gets farther and farther from the surface of the moon, its speed gets closer and closer to zero, so its kinetic energy gets closer and closer to zero, so that it has no leftover kinetic energy when it's really far from the moon. So strangely enough, I'm going to take my system again to be the rock plus the moon with the gravitational internal force associated with the potential energy. And my initial state is going to be the launch. The final state is kind of peculiar. It's going to be, the final state is when the rock is infinitely far away and it has zero leftover kinetic energy. In other words, it's going at zero speed. So it just slows to a crawl, but it never turns around and comes back. It just goes slower and slower and get closer and closer to zero as it gets farther away. Okay, so that situation, that launch speed that's just right at the cusp there where it never comes back, is called the escape speed. So this would be the escape speed for the moon. So in that case, again, using the same work-energy relationship that we've been using, there's no external forces. Again, if the gravitational force is internal, no external forces to do any work. I do my difference in 1/2 mv squared, and well, let's talk about that in a second. This is the change in kinetic energy. This is the change in potential energy. And again, I'm being very careful about those minus signs and putting in parentheses so I don't miss anything. The final state is one infinitely far away. So I'm going to take R final to be infinity, or a really large number. And when you divide by a really large number, you get something that goes to zero, right? If you divide by larger and larger numbers, you get smaller and smaller results. So this goes to zero for the final state. Similarly, when it's really far away, we're assuming that its speed is going to go to zero. That defines the escape speed for the initial condition. So we want our final speed to be zero. So this first term also goes to zero. The initial condition is that it's 1 moon radius away from the center of the moon. So it's at 1 r is equal to r moon in this case for the initial. And this v initial is what I want to solve for. And now it's just a matter of doing some algebra and keeping track of those minus signs or simplifying them. And when we do that, we find that if we launch it up with a speed of 2,400 meters per second, it would keep going and going and never fall back. But if we launched it with any slower speed, it would eventually fall back to the surface of the moon. All right, let's take a break after that.